for the optimal adversary for general K. So the conjecture for fixed delta is complicated, so I'll just state the version asymptotic as delta goes to 0. That it's what we call a comb strategy. So you advance experts, the odd ones or the even ones, equally likely. So either you assign all of these gains of 1 or all of these gains of 1. And this seems in simulations to behave very well, but the only case where you have a full proof is 2 and 3. So let me tell you something about the case of 4, which is where we don't have a full proof of optimality, but we have been able to analyze exactly this comb adversary. So in the comb adversaries, advanced experts 1-3 with probability half and 2-4 with probability half. So here they are. Okay, so advancing means getting a gain. Now when 1 and 2 coincide, and then say if 2 moves ahead of 1, then I have to switch identities. Because the leader is defined to be 1. So we get to this picture. So if you look at it, the distance between 1 and 3, so if I keep the record of their gains, that distance is always the same as the distance between 2 and 4. So because of that, it's enough to just keep track of 1, 2, and 3, because I can always then compute where 4 is. And then we can map to the following slightly simpler process, which is random walk of a particle between a fixed wall and a moving wall. So this heavy wall on the right doesn't move, and the particle bounces off it. But the other wall, when the particle hits it, it moves the wall. And then it turns out that the regret comes out to just the number of times this particle visits the fixed wall. And first, when we analyzed this, we first ran simulations, and we got this.
Sorry, I don't quite understand. So what is the movable wall doing if it always moves when the particle hits it? So it's almost as if it were not there.
But but the particle still gets reflected. So
it bounces back. I see. Yeah.
Okay. So there is, it still sends the particle back, but it also moves. And we first got the result for simulations, and it took us a while to analyze this. But it turns out, and this paper is on the archive, so I'm not going to go into the calculations, but they're actually very interesting calculations. So one has to understand the class transforms of exit times of random walks from various strips and combine them in the right way. And when we did that, we first got this series, which is the Riemann sum for this integral. And well, this integral is actually one that is calculable and gives this. So this 0.785 is actually just pi over 4. But as we've done this analysis, each time we increase the number of excerpts by 1, the amount of work we had to do is squared. So we're not about to attempt the k equals 5 case without further insights.
Excuse me.
Yes.
In the k equals 4 case, just comparing it to the k equals 3 case,
Yes.
I would have guessed group the top and the bottom together and the 2 in the middle together. Is there some obvious reason why that isn't the next way?
Okay, this is so we're looking at the max minus the average. So the max is actually 1 when compared to the average. Now, if you compare the max and the average, when the particles are not colliding, then both the max and the average are a martingale. So, I mean, the average is always a martingale because the thing is balanced. So it means okay, I should let's put it. Okay, they're martingale when you subtract the constant. So what I want to say is that because of the balanced condition, the max and the average typically advance in expectation the same amount. The only case where they differ is when we have 2 particles in the leading position, 2 experts in the leading position, and then the max gets a push because if one of those two moves forward, he becomes the max. And so we get that the max minus the average stops being a martingale exactly in times when 1 and 2 collide. So the strategy for the adversary in order to increase the regret is actually to design a process where 1 and 2 will collide as often as possible. So and so ordinary random walks collide about order root t times, but here the goal is somehow to arrange to improve the constant by suitable arranging the particles. Now when you put, so in order for 2 to catch 1 frequently, you want 2 to get a push from behind. So he will get pushed. When he collides with 3, then 2 will be pushed. So, because of this logic, it turns out you want, so one think of when kids build the soccer teams, right? So they take the best player, and then to make a balanced team, the second player is in the other team, and then so they often will alternate. It's not the unique solution, but it's one that achieves the approximate balance. Okay, so I'm going to move to the second part now. Unless there are any questions. So second part, I want to discuss a problem in the harder setup of bandit feedback. So so here we're very ambitious. We're trying to find the optimal constants and the optimal algorithm. In the bandit feedback, much less is understood. So let me go to this. This is joint work from with Ofer Deckel, who's at Microsoft and actually got me interested in this whole subject. Jian Ding, a former student of mine now in Chicago, and Tomer Koren is in the Technion. And again, we have a player and an adversary. And again, there's this distinction between adaptive adversaries and oblivious, and bandit feedback, where the player only sees the loss or gain associated with his action, and full feedback, what we studied before, where the player sees the losses or gains associated with all the actions or all the experts. And again, there is even in automated news servers, there's a question what to put as a top headline, and you want to put as top headline what people want to see, what people click on the most. So this is again an online learning problem, but it's typically one with partial feedback somewhere, not full feedback, because the consumer will click on one headline typically. Okay, so the abstract setting, we have again a T-round repeated game between the player and the adversary, and now we're going to think of losses rather than gains, but this is just a change of sign, and we're going to allow these to depend somehow on the past. Okay, so the player's cumulative loss is this. And now the regret takes this form. So because we're talking of losses, this is the same thing as just with the change of sign. So the best expert is the one with the minimal loss, and we chose ft at time little t, and this is the loss that the player incurred. Okay, and again, the goal is to minimize the regret. And I remind you of the multiplicative weights algorithm, where you put weight on I, which is exponential of minus gamma, the total loss until in the previous times. And the right choice of gamma yields the scaling root t log k, that's what we saw before. Now, in the multi-armed bandit problem, you cannot use this algorithm because you don't know, to maintain this vector of weights, you have to know the losses of all the different experts, and you only know the loss of the expert or the action you chose. Amazingly, this can be handled by just replacing the loss vector by an unbiased estimator, which is a vector with a unique non-zero entry. So you take, right, this is what you know from important sampling. So suppose at time t you chose action I, then you know the number LTI. So that's the feedback you get. You take this LTI and divide by the probability you assigned to choosing this expert. Right? So you had some randomized procedure to choose this expert. So you divide this, and at all the other entries you put 0. This is a random vector with a unique non-zero entry, but the location of that entry is random. And if you take expectation of this, you just get the vector LP that we were using before. So you just take this vector and use it as if it was the loss vector, which first looks kind of scary, but it turns out it still works, and it gives regret, which still scales like root t, but the dependence on the number of actions is worse. Now root tk instead of root t locally. This is a classical analysis from 2002 and refined by Odibert and Rubek in 2009. Okay, so what is the model we considered in this work? A model with switching costs, which is something both interesting theoretically and occurs a lot in practice. So when you go from, action 1 might be only, using one hedge fund manager, and moving to another one has some friction. Or it might be we have some robot in a plant, and we have to switch the robot to do another task. There's some cost. So many times there's a cost associated from switching actions. And here we're going to simplify and just assume this cost is 1, but to scale the cost. So in other words, we're going to add to the raw losses this extra indicator of a switch. Now what is interesting is that if there is another algorithm, not a multiplicative weights algorithm, but one by Kalai and Pampala, that in the case of full information says this really switching cost doesn't hurt, because they have a method which switches rather rarely between actions. It is, there's no big reason to switch frequently, because you're getting information in the full information case. You're getting the full information. So only if one expert develops a substantial lead on another, it is important to switch. So if there's just kind of small fluctuations of order square root of the time, then they don't mean much, and you don't need to switch. And this is formalized in this paper, and they show that in full information we have root t. But the problem in the case of bandit feedback and switching cost was open. So this is the case we want to focus on, switching and bandit. And here what was known was an upper bound of t to the 2/3. Let me explain that quickly. One thing we can do to control the switching cost is just divide the time into blocks of length b, and just commit ourselves not to switch during a block. Then the worst number of switches we could have is t over b, because that's the number of blocks. But this commitment does cost us something. So now we have t over b blocks, and the loss will be at most root of t over b. So I'm thinking of fixed number of actions. That's what a equals to. So we have square root t over b, but the loss per block now is not 1. It could be as bad as b. So we get b times this. So we get t over b plus root tb. And optimizing this, we choose b, which is t to the 1/3, and we get regret of order t to the 2/3. So this is the straightforward blocking argument. And for a long time, there was no lower bound better than root t, and no upper bound better than t to the 2/3. And this was the problem when actually Ofer Deckel approached me and said he thought that some more sophisticated stochastic process should be needed to understand this problem. So again, by this minimax principle, or this is really von Neumann, but a version of Yao, it's the standard procedure is to try to find a good distribution of losses that will, a good distribution for the adversary, which will give regret of order t to the 2/3. So for simplicity, let's focus on the case of two actions, but this does generalize. Okay, so kind of jumps to the answer, but let me quickly explain what's going on here. So the standard kind of losses that people used in the area are just IID losses. Now, if you use IID losses, then the player can learn without switching. So suppose, just to give a concrete example, suppose we have here losses x1, x2, and so on, which are IID. And here we have x1, plus minus epsilon, x2, plus minus epsilon, and so on. And this plus minus is not changing from round to round. So this is your one choice. Either they're all moved up by epsilon or all moved down by epsilon. Okay? So this will be arm 1, this will be action 1, this will be action 2. Now in the bandit case, the player never sees both of these losses, right? Because if he saw it once, he could know does epsilon come with a plus sign or a minus sign. But he always has to choose. Okay, so but he can just go for a long time without switching and just compute an average, and only then switch and compute an average, and this way decide whether he is better off on the top or the bottom, and without paying much in switching cost. So he will be able to, he will just need to go for time which is 1 over epsilon squared until he can distinguish the average of the top and the bottom. And so it's easy to see that this is not a very effective adversary. Now the other option that people considered is to use a random walk. So if St is the sum of xi I from 1 to t, where say xi are standard normal, then you could use losses which are S1, S2, S3, and so on. And here S1 plus minus epsilon, S2 plus minus epsilon, and so on. So this does better in some sense, because now you don't get any information if you don't switch. Because when going from S2 to S3, what happens? I'm adding a standard normal. When going from S2 plus minus epsilon to S3 plus minus epsilon, remember the sign here is fixed once and for all, then I'm adding the same thing. So I don't get any new information unless I switch. Each time I switch, I get some information, actually information of order epsilon squared, because I have to distinguish a Gaussian plus epsilon from a Gaussian minus epsilon, and 1 over epsilon squared such observations will suffice. The trouble with this is that if I really use xi, which are say standard normal as I wrote, then these sums become unbounded. So I'm only allowed to use losses that are in 0, 1. So I would have to really scale them down by a factor of 1 over root t, and this scaling will have a very serious effect. Now epsilon will mean something different, and this doesn't work either. So we have to combine the good features of both of these examples, and that's what's done in this example. So this is the actual loss process we use. So it's like a multi-scale random walk. At every time we add some, so the loss at time 0, say, is a half. The loss at time t is a new Gaussian plus the loss at some time rho of t in the past. But what is rho of t changes. It's not always t minus 1. So this is kind of a general scheme to define a type of generalized random walk. So the scheme, as I wrote before, L at time, the loss at time t is the loss at some past time plus a new Gaussian. You have to choose carefully this function rho of t. So the arrow here that you see is actually from rho of t to t. So just to get our bearings, the case down here is the case when rho of t is t minus 1. This is a case of a random walk, because each time I add the previous loss. And the problem is this kind of function is too big, so the loss here is a sum of too many terms. This case here is the case of IID losses. Okay, so each one is just the L0 plus an independent choice. This function is what we call too wide. So if I look at some intermediate point here, too many arrows cross over it. And what that means is if I switch at this point here, I will get too much, the player will get a lot of information from switching. So you have to find a function which is not too wide and not too deep. So that means for every node, you go back to the origin in a logarithmic number of steps. But also, if you look at the vertical slice, it doesn't intersect too many of these arrows, only a logarithmic number. And once you find some function, you're golden. So, okay, so with this, okay, so once you find such a function, I'll come back to this, you use the same recipe I did before. So you have one process, which is the blue process, and then you move it up or down equally likely by epsilon. So the point is, how many samples to estimate the mean of a Gaussian with accuracy epsilon? The answer is if the Gaussian has standard deviation epsilon, it's sigma over epsilon squared. So the question is, how much information do you get in a switch? So remember, in the IID example, when we have a switch, we can get a lot of information because there's a lot of past, before it, and future after. In the random walk case, when we make a switch, we basically get one piece of information which is worth epsilon squared. In this case, it's intermediate. We get just a logarithmic amount of information. So the function we are using is this one. So rho of t is t minus this GCD. What does this mean? Take t, write it in binary, okay, and remove the least significant bit. So this function, for any t, if you do a logarithmic number of steps, you will get back to 0 because you just have to remove all the bits. But also, it's not hard to see that this function will only, if you look, if you look at any point and ask how many arrows cross over this point, say here you get 2, and you always have at most logarithmic number of arrows. And these arrows represent the information you have, because whenever I do a switch here, then I get information by comparing this sample to this sample, but also this sample to that sample. But this will assure I don't get too much information, or the player doesn't get too much information. So I think, beyond this, it's a, maybe I'll say one more thing about this calculation. So what are the options for the player? He can either, so the epsilon that we're going to choose will be t to the minus 1/3. Okay. So the player could either switch enough times so he could tell the top from the bottom, but that is going to cost him, because if he switches, to tell the top from the bottom, he's going to need 1 over epsilon squared switches, and so this is going to be t to the 2/3. That's one option. The other option is the player can switch fewer times. In that case, he doesn't have enough information to tell the top from the bottom, and so with probability half, he'll be spending most of his time on the wrong side, and then he'll incur a loss. So the wrong action is worse by a factor epsilon from the better action, so he loses order epsilon t, which with this choice of epsilon again gives t to the 2/3. So whatever the player does, he will lose order t to the 2/3 up to some logarithmic corrections that I'm ignoring. So the way we first arrived at this process was actually by a different route, starting with the branching Gaussian random walk and doing a depth first search on that, and then, when we understood better why this worked, we brought it into this form. If I had more time, I could tell you more about that, but I won't. And just maybe finish by saying that we can also conclude that the original algorithm, even if you don't have switching costs, the original, any algorithm that works well, like this X3 algorithm that gives regret t, might on some inputs, like this input, have to switch many times, order t times. And we also understand what happens when you have k actions, so then this gets multiplied by k to the 1/3. So that's the effect. So I focus on k equals 2, but it can be extended. Okay, thanks for your attention.
Questions?
What, in a real life example, what is a source of a switching cost? What kind
So
of
I mentioned some. I mentioned some examples. Right? So again, one place this is applied is in stock market examples, and they're always, if you switch from one stock to another or from one stock advisor to another, there's some friction, there's some switching cost. But in actually about half the applications, just doing the same thing you did yesterday is easier than doing something new. So there's some cost. So you switch suppliers. You have two. You're a purchaser and you have two suppliers. Switching suppliers has some cost.
Yeah.
Draw up new contracts. Yes. Yeah. Sorry.
Can I ask you about this exotic random walk that you wrote, where you're not adding all the previous terms for a certain number of? So you had some kind of a scaling limit for this kind of a random walk as well?
Yes.
Yeah.
There is a scaling limit for this, and okay, this is easiest to understand from the kind of branching picture that I've omitted. But maybe I'll draw this very quickly. So you just assign say weight 0 to the edges going left, and Gaussian weights to the edges going right. Okay, and now and see at the root you put some constant. Okay, and now you just okay, maybe I'll put this at the root. Now at every vertex, what I'm going to put is the sum of the weights along from the root, including this root weight, to this vertex. And then I'm going to just move like this along the leaves of the tree. So when so if I'm here, I'm adding these, I'm adding these two Gaussians. Okay, so if you track the behavior as you move left to right here, you'll have exactly that kind of multi-scale random walk I was looking at. And then if we use the known behavior, scaling limits for branching random walks, we can infer the scaling limit for this process. I mean, it's not something we needed in this work, but it can be done. And this point of view can also explain, some of the arguments I was hinting at.